Hello again, fellow programmers, to this course and problem solving for PLC Animator. So, today we're finally going to solve our first exercise, which I personally chose for you guys. Now, we're going to analyze our very famous Hello World for industrial automation. Ready, guys? Up and at 'em. First off, we'd like to solve. I was trying to analyze which exercise or which drill I can solve with you guys. And I'd like to start with industrial fans. When we open our Animator PLC, the first exercise is going to be the public street light. If we click on our right side twice, we're going to find industrial fans. It's our first exercise that we're going to do together. Okay? Now, what do we have here? We have three fans, and all we want is to power on a fan, and I'd like to power on my fan with a touch of a button. So we would need an input and an output. Now, which one are we going to choose as an output? Let's choose our biggest fan and make this O semicolon 0.2. That's our first instruction. Identify input and output. Which input are we going to direct now? Because here I'm not getting any input at all. Okay, so if we move along and if we simulate or we start our simulation, sorry, our PLC Animator software is going to assign to us visual aid, and it's going to turn our programming instruction, which have been predefined on our left side, which I'm going to select here. Everything that we have here is going to be changed automatically to simulation mode, to our input. And we have some indicators here, but these are outputs. So these are only for support. So all we are really interested in is this. These are directed push buttons. Now let's say that we already connected each pulse to a specific input for our virtual PLC. Now this is already done, guys. So we're already avoiding this physical exercise because we don't have a physical PLC. But we thought about this specifically for you guys. So let's suppose that all this is directly connected to our PLC. This is already connected also. And each one already has its assigned input. Okay? So then, our exercise consists of going to a button and we're going to start our motor to start it up. That's our first instruction. Okay? Now, for this, I'm going to remove or I'm going to get out of simulation mode, and I'm going to select my first contact, which is normally open, and I'm going to select it. And we'll notice that the contact is being lit up. So this means that it's already being selected. If there's no illumination light, that means that I need to click it or select it with my mouse or my hand or whatever. So we select it, and on our segment to start our ladder diagram programming, we're going to select an empty space. So we're going to leave it in second box. Now we'll see that it's asking us for an instruction. So I know already what instruction you need. But where are we going to direct it to? So we're going to select our input, and also I'd like that for my button 0 with my E pulse 2.02 semicolon 0.0. I'd like that when I select it to light up our output, A to number 2. So I'm going to move my camera so that we don't get lost, and I really would like for us to identify where we're clicking or where we're selecting it. So it's going to be dynamic as far as where I'm going to move on this side. Okay. So in theory, we have our program ready. So as we said, when we push our button, we're going to get our signal so that we can start for signal number, our output number 2. Okay, so we're going to start with our simulation. We click on our upper right button where it says start. Click here. And we're going to notice something. I had previously said that in ladder diagram, it goes from left to right and up to down. So we notice here that if we energize or we get the signal, our coil, in theory, they're going to start moving or something is going to happen. Now, for these moments, we don't really have a signal from left to right, which means that this contact is open because we're not pressing it. If we were to press this button, then our signal would flow and in fact would energize our motor. Okay, let's see if this is true. So we press our button, which is on, and so this means that it is working. So the problem here is that we're not really, uh, that button is not, we're pressing it, but as soon as we stop pressing it, this output is going to de-energize because we are respecting the logic. Because I'm saying as long as I press my button, you're going to energize. And I'm pressing this, it's a pulse. And it's energizing, but it's also a pulse. It's on the same time as the button, which is normally open. Now, let's analyze this push button, okay? So this that we have right here as I semicolon 0.0 would physically be a very similar button, but it would be the green one. This is a push button. And if we notice, what I mean is if I press the button for a certain amount of time, it's going to be energized for the coil, or it's going to start powering on my motor, which in this case is the fan. But as soon as I stop pressing it, as soon as I stop pushing it, it's going to get that signal, and therefore it's going to stop. The fan is going to stop. It's going to stop moving. Now, how do we solve this problem? There's some ways, and the most common one, if you come from a more advanced knowledge, you know what enclaving is. But I'd like to show you a Animator PLC function. And this function is physically to change it or simulating for a normally open contact. But the pulse is going to be different. This is a selector. Now, if you notice, it's a two-position selector. When it's in certain position, it is going to stay in that same state. But it's already physical. So physically, it's going to maintain. Whether I'm powering off my fan or I'm powering off my fan. And it's going to be energized because it is allowing for the flow or the passing of signal or energy. Now, where is it allowing it to? To our PLC input. So then it is respecting our program because it's saying as long as you allow for my voltage flow or my signal to go through, you are going to stay on. And this is staying on actually. Now, at a programming level, what did we do? There is a part below our push buttons where we can select between an object, an input type to another. Now, the first type is push button. The second type is a selector. Now, we select our selector, pardon the repetition. So without the need of an enclaving, this is for practical solutions or for practical issues. So once on the field, you're going to know what's the best solution that you can implement. This is solution number one, which is directly changing our physical button to a selector. That's going to be the easiest part. The easiest part here is at a programming level. But now, ideally, it would be to run an enclaving. And the following way in which we can energize our motor, however, without the need of having an engineer or an operator pushing our button all the time so that so that coil continues being energized. And that is through our parallel instruction, or as many of us know it as the famous enclaving. So for our software, when we select that instruction and we select that we insert it in an empty space, automatically or predefined, it's going to be established through our programming, which is going to send it to our upper part in the center of our laddered language programming. So therefore, this instruction, we're going to move it within. So we can eliminate it momentarily. And that's perfect. Now, what does this enclaving do? It's indicating that I have my first condition in my upper line in which we need to pass our signal from left to right. In other words, we should energize our output or run certain activities. In this case, for example, power on my motor or powering on, which is our first option to have our conditions in our upper line, our top line. To comply with these conditions for our second line, or our third line, or fourth line. So it all depends on what we can add. Depends on what we can add below these conditions, which we also want to comply with. Okay? Now, what do I mean by this? I'm adding here that this be our button that is directed to our concentrated button and our 0.0. But also through our enclaving, we're asking it that that it listen to us for our following conditions. But this is only an option for us or so that the energy flows or the signal can comply with the bottom part. Now, this is a path and this is a different path. Where is it going to comply? On the top part or the bottom part? Whichever complies, I wish or I want that you please energize our coil or 2.0.2. Now, how would this work? I would direct it here, for example, I'm going to direct it to my second input. So I'm going to simulate if it complies with my first condition for my upper line, it's going to power on my motor or that coil. But it can also energize if it complies with the second condition that it's indicating, which is pressing whether it's a button 0 or button number 1. So whichever it's complying with, I want you to energize it. So we change it to selector mode, as I had previously stated, and it's going to keep energized. So additionally, if I maintain my condition for my line, for my parallel, for my enclaving, it's also going to stay energized. Now, what would happen if we assign the signal for both conditions? It's going to be the same thing because ultimately it's going to comply with what we're indicating for the first line or for my second line. Okay? All right, perfect. Now, this is how the line works in parallel. So let's stop this. And now, how am I going to keep it energized thanks to this parallel? Well, it's all about directing our output, which in this case, or in this case, it's about directing it, which in this case is 0.2. Now, what am I indicating? Now, it's saying that whenever I send out a pulse, it does power on, momentarily at least, and very quickly. But ultimately, physically, the signal is very quick, very strong. Electricity works very fast, but it does detect that there was a status change that is really moving. So we can activate it for a little while, but at least it's activating. So with this, I'm indicating my PLC, my virtual PLC or physical PLC. I'm saying that while my coil stays on, if it detects that it's on, then keep it energized. So first we send a pulse. It's going to power on for a certain thousandths of a second for a very short time. But here I'm detecting this. It's noticing this. So as an input, I'm simply playing with my memory. So I can assign an input, in this case, to a normally open contact, but it's all depending as an indicator. So at a program level, it's about me playing with my algorithm. So remember, this is pulse, and I'm going to assign a pulse. So now I'm indicating my program saying, all right, so it's energized. It has energy, and I'm detecting that signal. All the while, or while I have as a second option that my coil has energy, you are going to stay on. So let's say that this is like an infinite loop. Literally, the same output is enclaving with the signal that it's been chosen. So we don't have to modify or change our button. So our push button for a physical button, a switch type. So here it is physically enclaving because the device is allowing for the flow for our signal or the blocking of the signal because ultimately it is a selector which sounds like a selector. And with our program, our algorithm, it is already simulating that enclaving. So this we already checked through our Animator PLC when we analyze all these instructions. Now, If you wish to be check this more in depth, you can check the enclaving. Okay. Now, what is needed to complete our hello world? We need to stop it. Okay. Now, let's stop with a second button for our fan. Now, for this, we would need a normally closed button wherever you wish to add it. Okay. You can add it at the beginning or at the end, but it shouldn't be within these enclavings. We should stop our fan, but I'm going to add it at the beginning. I'm going to add it to our regularly closed contact, but I'm going to direct it to another input. In this case, input number 1. Now, if you notice, we are assigning our first input, which is start. Our second one is going to be pair. Now here, start and stop. Sorry, start and stop. So behind our buttons or our pulse, we're going to input our blocks for normally open or normally closed. When they are emergency stops or any device where we have to stop our machine, we generally recommend using normally closed contacts. And we need to make them match with our physical PLC inputs generally. Okay? So then, knowing all this, now it works the other way around. When they're normally closed, in this case, for example, our red button for stop, we are going to connect physically as normally closed on one end of my block, and I'm going to connect it to my PLC input. So I'm going to close my circuit, which means that I'm always going to be getting signal, and it's always going to be getting something unless I interrupt it. So if I press my red button, it's going to interrupt it, and it's not going to allow for my signal flow. So let's see if this is true. Now here, I'm not going to press anything because I wish to demonstrate. If you see here, our flow is always going to happen. My line is it's always going to indicate that there's something here. So if I press it, it's going to stop. Okay? So when I press this, that contact is going to open. So if it does open, it's not going to allow for my signal. So now I'm going to start and it's going to stay open. And if you notice, it's not listening to my upper line. It already did it. But then I stopped pushing it and it's now listening to my enclaving on the upper side or the upper part. If this button that's assigned, as we know that this is assigned as a stop button, if I press this, it's going to stop for the whole fan. So there's going to be an error if we make a mistake. And this button, I'm going to add it to my upper part. It's not going to listen to me because it's only going to stop for this line on my lower part. But it is going to listen to me on the top part. So I wanted to completely stop my fan. So that's why this fan, so that it really stops and that it keeps energized for my fan. Okay? the energy for my output number 2, which is my biggest fan. So let's play around a little bit with my selectors. Okay. Now I'm going to keep enclaved my fan and it's going to work. If I were to activate my output, what I was saying, what I said, it doesn't matter how badly I want to energize it. This is for security reasons. If I want to energize my fan, it's not going to listen to me because I'm stopping the signal flow. So that's why it's recommended that we need to be very careful where I'm going to add my permission to stop my system. So what do you guys think? This was our first Hello World. If, believe it or not, this is the industrial automation Hello World. We know that there's one for automation, another one for IT and systems, but this is our very famous Hello World. Start and stop our motor. And of course, running and enclaving. This is our first exercise. Congratulations if you got to this point. If you're just now starting to discover this automation point, congratulations, guys. And we're going to continue working so that little by little we can start solving more complex exercises. And so that way you guys can start solving problems. And when we come back, if you have any questions, you can ask me to see how I solved this problem. Or if you were unable to move forward because of an instruction, or you're confused, or simply wish to analyze a different way to solve these instructions, then you're going to be able, you can come back to me and I, with these bases, or with this basis, you can basically become independent programmers. Okay? Big hug, guys, and thank you very much for your time. Have a great day.